We have seen different steps involved in the design of payments. Now we will see different inputs for the payment design, and first we will focus on traffic factors. Professor Neetu Roy has already explained in detail about various traffic factors that are considered for the payment design. Here we will focus only on specifications related to IRC 37 2018 design. One of the main factors that is used for the design is the traffic volume. So we consider a vehicle that has a weight greater than 3000 kg in the design of payment. It means that any vehicle that has a weight less than 3000 kg do not induce any damage to the payment. So we need a present number of vehicles and a projected number of vehicles to compute the number of repetitions that is used throughout its payment life. So we represent the number of vehicles in terms of commercial vehicles per day. Moth has suggested 16 different class of vehicle using a payment and with 4 different axial configurations. So these are the axial configurations that Indian Highway has. We can see 4 different axial configurations that includes single axial single wheel, single axial dual wheel, tandem axial and tridem axial. So these axial configurations are important for determination of a vehicle damage factor and for the determination of stresses and strain in the payment. So you know that the stress and strain in the payment depends on the type of axial configurations. IRC 37 uses tandem axial as 2 repetitions of a single axial dual wheel and consider tridem axial as 3 repetitions of a single axial dual wheel. So these are 16 different classifications of a vehicle that is using an Indian highways. You can see that these classifications are grouped under 3 major groups. One is a rigid truck, and second one is a semi-rigid truck, and third one is a tractor trailer units. So each truck has a different number of axials varying from 2 to 6 and different axial configurations. For example, 2 axial truck has single axial single wheel as a front axial, single axial dual wheel as a rear axial. Now if you consider single 6 axial truck, you can see 2 numbers of single axial single wheel and 2 number of tandem axials here. But IRC consider 1 tandem axial as a 2 repetition of a single axial dual wheel. So you have total of 6 axial here in this truck category. So you can have 16 different classifications or arrangements of an axial, and number of axials varies from 2 to 6. So we measure traffic volume following IRC 9 guidelines. So IRC 9 states that you count the traffic volume continuously for 7 days and for 24 hours and take an average daily average, and we get the average daily truck traffic, and this average daily truck traffic is used in the computation of number of repetitions of a standard axial load. So we also need a vehicle growth rate. If the number is not available, IRC suggests to use 5% as a vehicle growth rate. So now number of vehicles that is acting on a payment throughout its design life or n year is given by this expression 365 into 1 plus r to the power n minus 1 into a divided by r. Here r is a growth rate, n is a design life and a is a average daily truck. So now if the number of lanes is more than 1, this total number of vehicles will be laterally distributed. So the lateral distribution factor is a 1, the next factor to be considered, and it governs the number of vehicles per lane. So this is the IRC suggested lane distribution factor or lateral distribution factor. We can see that depending on whether the highway is a divided highway or undivided highway, we use vehicle computed from both the directions or from one directions. In case if it is an undivided highway, use the sum of vehicles from both the directions and use the lane distribution factor from as a factor from this volume considered in both the directions. So in case if it is a single lane, lane distribution factor is considered as 1. It's an intermediate lane, 0.75 times sum of vehicles moving on both the directions. 2 lane, 2 way, it's a single carriageway, so it is 0.5, and if it's a 4 lane, 2 way single carriageway, so it is 0.4. So all these factors are considered as from the sum of total vehicles flowing from both the directions. In case if it is a dual carriageway or a divided carriageway, so these factors are based on the vehicle from one directions. You can consider both the directions to have a equal volume in case if you do not have a data to segregate. So, 0.75 into number of vehicles flowing in one direction gives you the total number of vehicle in one lane if you have a 2-lane carriageway. So, if it is a 3-lane, lane distribution factor is 0.6, and if it is a 4-lane, lane distribution factor is 0.45. So, when you multiply a number of vehicle by a lane distribution factor V, it gives you the number of vehicles per lane. So, now we also need to convert this number of vehicles in terms of standard axial load repetitions. So, for this we use a conversion factor called vehicle damage factor or VDF. So, VDF is a multiplier to convert any commercial vehicles having different axial configurations and different axial weight into an equivalent number of standard axial load. So, one standard axial is considered as 80 kilonewton single axial with a dual wheel. So, on multiplying number of vehicles with VDF, we get number of repetitions of a standard axial load. So, we need an equivalency factor here. So, this equivalency factor computation depends on the axial configurations. So, with single axial with a single wheel on either side has an equivalency factor of axial load in kilonewton divided by 65 raised to the power 4, and you know the importance of this power 4, and Neetu Roy has already explained you about this importance of power 4 here. In case if it is a single axial with a dual wheel, the equivalency factor can be axial load in kilonewton divided by 80 kilonewton raised to the power 4. So, you have it for a tandem axial and a tridem axial. So, this gives us the equivalency factor for any axial load. Now, VDF is nothing but the sum of all equivalency factor corresponding to number of axials in a vehicle. So, for example, if a front axial of a vehicle is a single axial single wheel type and it weighs 6.5 tons. And the rear axial is a single axial dual wheel type and it weighs 8 tons. Now, what will be its vehicle damage factor? It is only one vehicle here. Now, front axial is a single axial single wheel. So, its equivalency number will be axial load in kilonewton divided by 65 raised to the power 4. So, it is a 6.5 tons. So, you have 6.5 divided by 6.5 raised to power 4 as a equivalency factor for front axial, and equivalency factor for the rear axial is 8 tons divided by 80 kilonewton. If you convert into tons, you will have 8 again raised to power 4. So, you will have 1 plus 1 or it is equal to 2. So, this vehicle with a front axial of 6.5 tons and rear axial of 8 tons is equal to 2 number of repetitions of a standard axial load. So, when you multiply the number of vehicles per lane by the vehicle damage factor F, it gives you the number of repetitions of a standard axial load. So, N design here is a number of repetitions of standard axial load. So, for computation of a vehicle damage factor, we need an axial load. So, axial loads are measured by using a static measurements. So, you have a weighing pad here and vehicle stands over the weighing pad and we measure a wheel load. When wheel load is multiplied by 2, we get an axial load. See, again we cannot consider all 100% volume here for the computation of an axial load. So, IRC suggests the minimum sample size for conducting an axial load survey. So, it all depends on what is the traffic volume there. If a number of commercial vehicles per day is less than 3000 vehicles, you can consider the sample size to be 20% of a total volume. So, when it is between 3000 to 6000, it is a 15% of a total volume, and if it is greater than 6000, 10% of a total volume, with the minimum numbers to be 600 and 900 commercial vehicles per day. So, when you have a number of axial loads, now these axial load data can be grouped at the different interval depending upon the axial configurations. If you have a single axial configurations, you can group at an interval of 10 kilonewton, tandem axial configuration 20 kilonewton, and the tridem axial configurations to be 30 kilonewtons. So this is a typical example after grouping of data. So you can see that single axial from different class of vehicles are combined and are grouped here. So you can see the group interval here is a 10 kilonewton. So you have a number of repetitions of axial load that has a weight between 185 kilonewton to 195 kilonewton. This is 70,000. So you can see the grouping interval for a single axial single wheel or dual wheel to be at the interval of 10 kilonewton. For a tandem axial it is at the interval of 20 kilonewton, and for a tridem axial at an interval of 30 kilonewton. So this grouping will help us to reduce the data size and it will be easy for further computations. So the next input that we give it for the design is the material functions. The main material functions that we need for the design is modulus. We know that the layers are assumed as an elastic and we compute the stresses and strain. So instead of an elastic modulus, we consider here a resilient modulus for the design purpose. So we use resilient modulus for hard mix asphalt layer, granular layer and soil layer. In case if we use a cement treated base layer, we use an elastic modulus there. So we will see in detail about this modulus for different layers. So IRC suggests to measure the resilient modulus of a subgrade soil following AASHTO T307. So in case if you cannot measure a resilient modulus value, there is also an empirical equations available relating resilient modulus to a CBR of a soil. So if the CBR of a soil is less than or equal to 5%, the resilient modulus is 10 times the CBR, and if the CBR is greater than 5%, the resilient modulus is given by this exponential functions. So now we can relate a resilient modulus to a CBR value. So suppose if we have 1 kilometer stretch of a road and we have 1 CBR for every 100 meters and totally we have 10 CBR value, all 10 CBR value may not be the same. In such case, what CBR value we will use it for the design here. So it all depends on what is the traffic volume here. If the traffic at the corridor is more than 20 MSA, we go for 90th percentile CBR. If the traffic at the corridor is less than 20 MSA, we go for 80th percentile CBR value. So you compute the percentile CBR here and use it for the design. If we have a subgrade divided into sublayers, we may have different CBR for different sublayers. But in a design purpose, we consider subgrade as a single layer. Now again the next question is which CBR to use it here. So it all depends on equivalent CBR value or equivalent modulus value. So suppose if you have a two sublayers, each layer has a modulus, two different modulus E1 and E2. So you perform a stress strain analysis and compute the vertical deflection at the surface due to a wheel load and equate the surface deflection to a single layer structures with a modulus E. So the surface deflection computed here will be same as the deflection here. So that what will be the modulus that causes the surface deflection of delta here. So delta can be computed using a software here and modulus can be estimated using this expression. So resilient modulus relating the surface deflection value here is given here. Here mu is a Poisson's ratio, P is a contact pressure. We use 560 kilopascal as a contact pressure, A is a contact radius. So if the load is 40 kilonewton and if the contact pressure is 560 kilopascal, you can compute the contact radius from the load and pressure and you will find it out to be 150.8 millimeter. So now this we use a equivalence modulus for the design purpose, and there is also a limitation considered in the IRC 37. So IRC recommends to limit the use of modulus value to 100 megapascal. Next is a modulus of a granular layer, that it can be a base layer and a sub-base layer. We know that the modulus, that is a resilient modulus of a granular layer, is a pressure dependent. So, if the depth of the granular or a subbase layer is going to change, the modulus value is going to change. Anyhow, IRC uses only one single modulus here for the entire depth, and that modulus can be computed using an empirical equations given here. So, this modulus is a function of height or depth of the granular layer and modulus of the subgrade layer here. So, MR support here represents the modulus of a subgrade layer, that is an effective modulus to be considered here. Now, if both base course and subbase courses are made out of a granular layer, you can consider both to be the same one single layer and compute the modulus here. So, but one thing we have to ensure that the subbase what we are providing above the subgrade layer should be sufficient enough to take the load and prevent the rutting of a subgrade layer during a construction process. So, what we typically consider is, we consider 10,000 repetition of a 40 kilonewton load to be acting on a subbase layer during constructions. So, this 10,000 repetitions of load may induce rutting on the subgrade layer. So, the thickness of a base course should be adequate to prevent rutting on the subgrade layer. So, if the base course or a subbase course are a cement treated, the elastic modulus of a cement treated base and subbase can be computed using this empirical equations, that is 1000 into unconfined compressive strength of a cementitious material. So, when you compute using this equations, you may get the modulus in the range of 2000 to 6000 megapascal, but IRC restrict the modulus usage of cement treated subbase to the value of 600 megapascal. And we also need a flexural strength or modulus of rupture of cement treated base for the computation of a cumulative damage in the cement treated base course. We characterize a bituminous mixture also by a resilient modulus value, and IRC suggests to measure a resilient modulus of different bituminous mixture in the laboratory following ASTM 4123 standard. This ASTM 4123 is a withdrawn standard where the resilient modulus in the laboratory is computed for an assumed Poisson's ratio value. The revised standard is ASTM D7369, where both Poisson's ratio as well as resilient modulus are computed from the laboratory test. Different types of layers used for two different bituminous courses are given here. One is for a surface course, another is for the binder course. We can see that the binder course commonly used is a DBM or bituminous macadam, in which VG40 binders are used here. So, depending on the type of binder, the modulus value is going to vary here. The surface course is a rut resistant layer. Stone mastic asphalt or bituminous concrete are commonly used, and depending upon the traffic intensity, either we use a modified binder or unmodified binder, and again depending on the binder here, the modulus value is going to change. This is an indicative value of resilient modulus value for different bituminous mixture. You can see that for any given mixture BC or DBM, depending on the type of bitumen we use, the modulus value varies, and the modulus is also sensitive to temperature. So, IRC suggests to measure resilient modulus value at 35 degrees Celsius and use it in the design. In case if you are designing a pavement for a snowbound area, you can prefer measuring a resilient modulus value at 20 degrees Celsius. These are the list of material properties that are used for the design purpose. For a bituminous mixture with VG40 or a modified bitumen, the resilient modulus used is 3000 megapascal or a laboratory tested value, whichever is lower we use that. Now, for a bituminous layer with the VG30, 2000 or laboratory tested value, whichever is lower is preferred here. For a cement treated base, we use 5000 megapascal, and for a cold recycled base course, we use 800 megapascal. For a granular layer or a crack relief granular layer, we use 450 megapascal. If it is a cement treated material but used in the sub base, it is a 600 megapascal, and if it is any unbound granular layer, so the resilient modulus value is computed based on the equations, that is the thickness of a granular layer and the modulus of the supporting layer. If it is an unbound granular base course resting over a exclusive cement treated sub base, then we consider either 300 or 350 megapascal. For a subgrade, again we have an empirical equations relating a resilient modulus to CBR value. You can use it in case if you do not have a laboratory determined value here. You can see that the Poisson's ratio of all the materials except cement treated base are considered as 0.35. If you have a cement treated material, the Poisson's ratio is considered as 0.25. So these are the material functions we use it for the design. So the now is the transfer functions that we use to convert the strain to the distress in the material. So we consider three different distresses. One is rutting for a subgrade, another is a fatigue damage of an HMA layer, and third one is a fatigue damage of a cement treated base. So this is a distress equations that is used to compute a rutting life of a pavement. You can see that number of repetitions of a standard axial load that pavement can withstand before the subgrade fails in rutting is related to a compressive strain at the top of a subgrade layer. So you have two different equations, one corresponding to 80% reliability and the other corresponding to 90% reliability. We consider 90% reliability equations for the computation if the traffic is more than 20 MSA, otherwise you can go for 80% reliability here. So either 80% or a 90% reliability, the structure of equation remains the same and only the constants which is used for computation of a number of repetitions of a standard axial load varies here for 80 and 90% reliability. For computation of a HMA fatigue damage, the number of repetitions of standard axial load that induces a damage of 20% of a area is for 80% and 90% reliability is given here. You can see that this NF also depends on the modulus value and the volumetric properties of a bituminous mixture here. So epsilon T is a maximum tensile strain at the bottom of an asphalt layer. So we compute this based on the stress strain analysis. For a cement treated fatigue damage, IRC 37 has given two equations, the one based on Australian practice and other based on AASHTO practice. The equation here N is equal to reliability factor into some constant here divided by epsilon T to raise to the power 12 is based on an Australian standard. See here RF is a reliability factors, you consider it to be either 1 or 2 depending on the importance of a road. So if you design a expressway, national highway, state highways or any important road that has a traffic more than 10 MSA, we consider RF to be 1, otherwise you can make it as a 2, that is you are increasing the life by twice. So N is nothing but the number of repetitions that cement treated base can withstand before it fails in fatigue damage. Here E is the modulus of a cement treated base and epsilon T is a strain at the bottom of a cement treated base. So this is an Australian practice. Now MEPTG practice of computing a number of repetitions of a standard axial load that cement treated base can withstand is given here. So it is classified based on the class or axial load group of a vehicle here I. So we have sigma T, which is a critical stress at the bottom of a cement treated layer. M RUP is a modulus of rupture, R it is a flexural strength of a concrete computed after 28 days of curing, and we call sigma T by modulus of rupture to be a stress ratio. So once you compute NFI for different class of vehicle, you can sum it up and compute a cumulative damage factor to be the ratio of traffic load repetitions by NFI computed using these expressions. So if you have a traffic load grouped in this way for a single axial, tandem axial and a tridem axial, so once you group the data like this, you can compute NFI for each class of axial and for each load group, and you can sum it up and compute a cumulative fatigue damage using this expression here. And we make sure that this cumulative fatigue damage value is always less than 1. So we design or determine the thickness based on this cumulative damage factor. So once we understand what are the inputs that we give into a payment design and how these strain computed are transferred to the distress in the payment, now we will see a software that is used in the computation of stresses and strain. So IRC 37 comes with a software called IITPAVE. IITPAVE considers payment layers as a linearly elastic layer and computes stresses and strain at different locations. So when you purchase IRC 37, you will get a CD, and when you open a folder in that with IITPAVE and IITPAVE updated, you will have a Java file here. First install this Java application file, and after installation open iitpave_start.jar. When you open it, you will get a window something like this, and this is the software which we are going to use. So in this you have two options. Let us design a new payment. So design new payment section. When you click it, when you open a new design, this is a window you will get it, and this is the only window available there, and you will have first as input as a number of layers. Once you define a number of layers, you will have a layer numbers listed here depending on the number which you give. I have given 3 here, so you have 3 list here. So you have a elastic modulus value, Poisson's ratio value and thickness value defined for each layer. You don't have a thickness for a final layer because subgrade layer is considered as an infinite thickness. So you give the elastic modulus value in terms of megapascal, and you give the Poisson's ratio value, thickness in terms of millimeter. So the next input is a wheel load given in terms of Newton. So if it is a standard axial load, so each wheel load is 20 kilonewton or 20 into 10 power 3 Newton. The tire pressure used for the granular layer design is 560 kilopascal, or in terms of megapascal it is 0.56. So this is related to the load input. Now what are the number of locations at which you need to find stresses and strain? So you give the number of points here. So I have defined the number of points to be 4. So you will see 4 different points to be listed after you define 4 here. So you need to give depth at which you need stress and radial distance at which you need stress. So now if I need a stress value at the interface of first and second layer, so it is 150 millimeter because the thickness of first layer is 150. Now if I give a radial distance of 0, it indicates exactly at the center of loading. Now if I give a radial distance of 155, it is between 2 loading systems. So if you define wheel load to be dual, so it is between exactly at the center of 2 wheel loads. Now second interface is at the depth of 400 plus 150, which is 550. So at the depth of 550 and at the radial distance of 0 and 155, we will get the stress value. So you can define any number of points as given here. So you can only consider as single wheel or dual wheel here for the analysis. In case if you have a tandem axial or a tridem axial, one tandem axial is considered as a 2 repetitions of one single axial, and one tridem axial is considered as a 3 repetitions of a single axial. So you convert it into a single axial and use one wheel or a dual wheel here. So once you give all input, when you click the submit button, after submission you will get this message, value successfully submitted. So once you submit, there will be an option to run the program. After you compile it, you will get the message done, and once you give this, so the final view results will be like this. If your view result is empty, you click view here so that you will get all the values displayed. Now in the result you will see number of layers, what we have given, modulus of each layer, Poisson's ratio value, thickness of each layer, and what is the wheel load we have considered, what is the tire pressure we used, the contact radius will be automatically computed, and whether we are using dual wheel or a single wheel. So these are the depth at which we are computing strains and stress, and these are the radial distance at which we are computing stress and strain. So you have 3 normal stress, sigma z, sigma t and sigma r, and 1 shear stress, and the 3 normal strains sigma z, sigma epsilon z, epsilon t and epsilon r is also given. You also have a displacement measured at that particular depth and radial distance. So, these are the inputs you will get it. Now, from this input you need to identify what is the critical strain that induces rutting or that induces fatigue damage, and you have to select and use it in the distress transfer functions. So, we also have a design catalog chart given in IRC for 6 different categories of cross sections that we have discussed already. This is one typical cross section for a granular base course and granular sub base course. So, granular base course is considered as WMM and you have GSB granular sub base course with two asphalt layer, one with the surface layer and other is a binder layer resting on the base course. So, these design charts are developed for a specific input data. So, most of the time these design charts may not match with our input data. So, you need to do a detailed analysis and compute or verify the thickness of the pavement.